Thank you. And I would like to, by the way, is the mic on? Okay, good. So I would first start by thanking the organizers for giving this wonderful opportunity to talk about our, I think a weird topic, this quantum thing. What I'm going to be talking about today is about non-reciprocal interaction, as you all love, but in a atomic scale, like 10 to the power minus 10, where I would like to argue that with a specific way of injecting a light to a material, you can make the spin-spin interaction to be really non-reciprocal, and as a result, by applying this to layered ferromagnets, we can induce what's called a non-reciprocal phase transition, where the time-dependent phase emerge. Before that, actually I'm going to be, I'm moving to Institute of Science Tokyo, which was formerly called Tokyo Tech, which just disappeared to become a Science Tokyo, 2 weeks ago. So that was an advertisement. So please say hi to me when you come by to Tokyo. Okay. So what happened? Yeah. Good. So yes. So I would like to start by thanking my collaborators, who's actually my very close friends, Daiki Otsuki and Rina Tazai, who are both solid-state physicists. She's a theorist who's working on a material called Kagome superconductivity, which she has a pretty famous work on that. And also together with Daiki, who's actually an experimentalist who's using a technique called ARPES, where he's usually shining a light to a material and see what the electron states are. But this is a pure theory work, but they have been very helpful in yelling at me when I say something crazy. Okay, so. Is that a fish? Oh yes, it is a fish. We went fishing. Okay, thank you. This is online on. Everybody in the world can see this, right? Okay, good. Okay, so because probably I'm the only person in this workshop that's working on quantum materials, so I think it makes sense to introduce very briefly what it is. So solid-state materials, I think you all know that, all the solids that you see in daily life are something like that. There's many, lattice structure depending on the material. And also there's, you can make, people are now successful in getting a synthetic quantum system where they have a good control over controlling actually at each particle level, so that they have, and it's extremely clean, so that, which serves as a very good testing bed for the concept that has emerged in this solid state systems. And and because of the interplay between the quantum correlation effects and the topology, a very rich variety of quantum many-body emerges. Just to name a very few of them, like quantum magnets, superconductivity, and quantum Hall effects. Okay, so traditionally people have been interested in the equilibrium systems, but researchers have broadened their interest to out of equilibrium quantum matter. So pick your, which is due to largely fueled by the improvement of the experimental techniques. So pick your favorite quantum material of interest, and the people have been able to, for instance, drive the system strongly out of equilibrium and see what happens, or put in some engineered dissipation such that it can do something weird and interesting. This is, I would say, pretty much similar to what soft matter theories, physicists have been doing, where I think in these 20 years or so, I believe, that people have broadened their interest to active systems. So there's some parallel, right? And what's really interesting about these systems is that the quantum, there are quantum many-body phenomena that's unique to non-equilibrium systems. Just to name a few of them. One is something called photoinduced phase transition, where starting from an insulator, by shining light to that, it can suddenly turn to a metal. And that's by definition a non-equilibrium transition. There's something called discrete quantum time crystal, where by shining a light at some frequency, it bifurcates into periodic doubling state, which is forbidden in equilibrium, as proven by Haruki Watanabe and Oshikawa. So there's another weird one, which is called a measurement-induced phase transition, where the amount of quantum entanglement the system has, which can be quantified by something called a entanglement entropy, can have a transition by strongly measuring the system as a function of the strength of the measurement. It can have a transition from what's called a volume state, where the entanglement entropy is a function, is proportional to the volume of the system, to the area. So again, all of these are fascinating, interesting, especially because it's something that's unique to non-equilibrium. And again, this is pretty much similar to how soft matter physicists have gotten interest in active matter system, where you guys have shown and proven that there are non-equilibrium many-body systems that are unique to active systems. Okay, so as I hope that this made it clear that driven quantum systems and active matter have a common interest, where we would like to see the many-body phenomena that's unique to those systems, and which I was say one step forward and say that it kind of implies that there can be common concepts involved. And I think there have been many success, already in the field. For example, using the concept that's emerged in derivative quantum system called non-Hermitian quantum mechanics. I'm one of the authors. The non-reciprocal, there's a concept that emerged in the non-reciprocal, something called the non-reciprocal phase transition, which Christina and Ramin have had kind of simultaneously. And there can be robust chiral edge in the stochastic systems. I think Everin is probably going to talk about this tomorrow. And also, this is some shameless advertisement, but some frustration physics that is known in solid state physics, in fact, have a direct analogy to non-reciprocally interacting systems. And as a result, some phenomena that's known in the geometrical frustrated systems can also emerge in non-reciprocally interacting system, where I showed that something analogous to order by disorder phenomena or spin glass-like state will emerge, where the noise can sometimes induce symmetry breaking, which is opposite from what you would expect usually. Okay, less is done. That was from quantum to active, but people have been looking at active to quantum systems too, where there's an analog of quantum analog of clocking, and MIPS has been considered very recently. But this work is about using the concept of active matter to introduce non-reciprocal interaction to quantum systems. Okay, was that? So that's my introduction to the quantum systems. Okay, and that's my kind of mindset for this work. Okay, so I don't think I need the introduction for non-reciprocal interactions, thanks to this audience, but as you probably know, there are many, many systems that have non-reciprocal interaction in active, soft active systems, such as neural networks, ecological systems, within matter, and so on. Right. So just to give, a clue about what's going to happen, and is kind of relevant to my work, this work, let me introduce what is now called non-reciprocal phase transition. Okay, so let's consider two groups of non-reciprocally flocking model, which is separated into two groups. The blues are the A groups, the red are B groups. And A groups are ferromagnetically interacting, so they want to align and flock. B group is the same, but we allow JAB and JBA to be non-reciprocal. Okay, so A might want to align with B, but B wants to anti-align with A. And let's see what's going to happen. Okay, so in the reciprocal case, nothing that special. Okay, there we go. Okay. Okay. Oh well. It's not very clear. Sorry, but so if it's a reciprocal where with JAB and JBA to be ferromagnet, A and B will align, while like this. While if it's anti-ferromagnetic, it's going to anti-align. However, very interesting thing happened in a non-reciprocal case, which I hope it's going to work. Okay. Okay, my computer is probably heavy, but it's because A and B is chasing each other like this. The A and B is doing chiral motion. So there's a non-reciprocally induced chiral symmetry breaking. It's chiral symmetry breaking that occurs. And this is associated with the spontaneous G2 symmetry breaking, which cannot be explained from Landau theory. Okay? So what's special about this transition point is as follows. So if it were reciprocal, then you have two modes because there's two arrows. And we know that because of the system is U1 symmetry broken, you have a Goldstone mode. And because the system is reciprocal, you have a mode that's orthogonal to it, which is a damped mode. As you make the system non-reciprocal, these two eigenmode does not have to be orthogonal to each other anymore. And at the transition point is where what used to be a damped mode coalesce with the Goldstone mode, and which is called a exceptional point in quantum non-Hermitian mechanics language. But it's critical because the Goldstone mode is a zero mode. And because of that, anomalous phenomena would happen, such as like anomalously enhanced fluctuations, where the fluctuation diverges at 4-dimensional less instead of 2. As Sarah have nicely shown, there's a diverging entropy production rate here. And with a sophisticated diagrammatic techniques, Sebastian Diel's group in Cologne have shown that it's actually at 3 spatial dimension, it's going to make the critical point to be first order instead of second. So these kind of fancy phenomena can occur in non-reciprocal systems. So, and in addition to that, there are many collective phenomena that can happen in non-reciprocal systems, such as elasticity, long-range order in 2D, which I believe Sarah would at least briefly talk about. And more back in the ages, there are interest in understanding the role of non-reciprocity on controlling the neural dynamics. So my goal is to see whether these kind of interesting non-reciprocal phenomena can occur in quantum systems. Okay? So, and actually, I'm not the only one that's asked this question. And actually, in quantum optics community, the non-reciprocal interaction has been of interest from very different contexts. And people have shown, have proposed and implemented experimentally some sort of non-reciprocal interaction. Okay, so let me explain their proposal. So let's say this is a two-site model. So this is atom can hop from here, site A to site B. If it were a closed system, because the Hamiltonian have to be Hermitian, these have to be a reciprocal hopping. However, to make this non-reciprocal, what they showed was that to consider the third site C, that you don't really care about, and you put dissipation to the system. And on top of that, they turn on the gauge flux on this plaquette, which explicitly breaks the time reversal symmetry. And as a result of this, if you want the atom to hop from site B to site A, there's two paths. There's one site path where B hops directly to A, or there's site path 2 where it goes to site C and then to A. And because quantum particles are waves, it can have an interference effect. And therefore, by tuning the parameter in such a way that this gives rise to destructive interference, then you can make this hopping to effectively vanish. But because the time reversal symmetry is broken, the other way around, in this case, is going to give you a constructive interference. And as a result, you get a non-reciprocal hopping. And actually, this very cool idea has been implemented in several platforms. This is an example cold atom experiment where you do see this nice, non-reciprocal hopping. However, this is pretty challenging to make in solid-state physics. Synthetic systems have a very nice control over each atom level, but solid-state is an angstrom level, needs an angstrom level control, and this is pretty much impossible to do in solid-state physics. But to get non-reciprocity in solid-state physics, what should we do? And I think there was a hint in soft-acting matter, because as you all know, you don't need a gauge flux to give rise to non-reciprocal interactions. So what do? Well, I think, in my opinion, optical reactive matter is one of the most simplest examples that shows non-reciprocity, which is the following. So say you have two metals, two metal colloids, metal A and metal B, okay? And it's trapped in an optical trap. You put, you inject, let's inject light to this system. Then if the light shines to A, the light can be some partially observed and some are reflected. And the reflected light will approach B, and that's because of the optical force, it will give rise to something that's fair to call FAB. The same thing occurs for B to A. Okay, super slow. But this does not have to obey the Newton's third law. Why? It's because the absorption rate can be different. So if you set B to be a perfect observer, then there's no reflected light to A, so FBA should be 0, but FAB can be finite. So you can make this non-reciprocal. And actually, there's a nice experiment where this is a system that's trapped in an atom, and it's a bummer that it's so slow, not so smooth, but you see this nice chase and runaway motion that appears because of that. Okay. So what were the essential ingredients? So in my opinion, well, firstly, it have to break the detail balance. But on top of that, it was at least very helpful to have a field that mediated interaction. Because that way, the interaction, during the process of getting interaction, the system knows that the system is breaking a detail balance. So actually, I believe all the known ways of getting non-reciprocal interaction in non-reciprocally interactive matter, I think more or less these two ingredients are there in ferritic active and quorum sensing of living matter. So this leads me to the idea that why not do this in quantum systems? Because there are many systems that in quantum systems that have a mediating interaction. And by breaking the detail balance there, the idea is to make non-reciprocal interaction by doing that. Okay, so yeah, so just to make it clear, yes, in the non-reciprocally interacting in soft matter, you shine a light to this, and there's a mediating field that give rise to non-reciprocal interaction. So our idea is to make essentially the same phenomena happen in quantum systems. So in particular, we aimed at electrons in magnetic metals, because that had the best analogy to in our opinion, where you have spin A, spin B that is known to mediate interaction by having the spin wave propagate, but by injecting light in a manner that I'm going to introduce very shortly, shortly, it's going to give rise to non-reciprocal interactions. Okay. All right. So I think not many of you know how magnetic metals work, so let me explain slowly. Okay. So magnetic metal is a magnet that is a metal. Okay. And okay. First. Okay. And then so it's made of two elements of electrons. What's called a localized spin, which is consists of d orbital or f orbital electrons, which is responsible for being a magnet. And there's another electron that's also important, which is the conduction electrons, which is usually made of s orbitals electrons, which can hop around the atom. So this one cannot move, but these can. And and the point is that even in the situation where localized spin cannot interact directly, the conduction electrons can mediate interaction in such a way that by having this, what's called a CD hybridization, which gives rise to the spin exchange process, can mediate the interaction by exciting the spin wave on the the sea of conduction electrons that reaches the spin B, which you can show by integrating out the conduction electron degrees of freedom, you get what's called an RKKY interaction. Okay, was that clear? Good. So our idea is to dissipation engineer this by injecting light to this. So let me just give one step further detail. So in the localized spin, how do they exchange spin is the following. So this is the orbital for the localized spin, which is in fact made of electrons, because everything is electrons. And this is a conduction electron. And once in a while, this conduction electrons can decide to hop into this state. But because the electrons are Coulomb repulsively interacting, they raise, the energy of the state raises by the repulsion energy U. Then, because the system doesn't like that, they spit out one of the electrons immediately. But because what used to come into downspin can spit upspin, there can be a spin flip process. And as a result, you get this spin exchange interactions. So our idea is to inject a light. Okay. Come on. Okay. Yep. To remove the electron that selectively, by shining a light that couples to a very dissipative unoccupied orbital, such that whenever the state is in a double occupied state, then it's going to make the electron decay. Okay. And that's how that's how the system knows that the system is out of equilibrium. Okay. So, okay. So, I have 5 minutes. So before I go on to, so before the time is up, I think I'll try and give all the necessary information for you. So, so this is what we showed microscopically. So in equilibrium, what you can show is what's called the Landau-Lifshitz-Gilbert equation, which is consists of this Hamiltonian part and the Gilbert damping term, where it's a friction term for the spin. Now, by shining light in a particular way, I mean, it gave rise to this additional dissipation-induced, I mean, light-induced interaction that is non-reciprocal in general. And as a result of that, so heavy and it's pretty annoying, but okay. Yeah, so as a result, the aligned phase by putting, by applying this idea to layered ferromagnets, it can have a transition for either aligned to anti-aligned or aligned to this chiral phase. Okay. So for next, okay. Don't know how many of you are interested in the formalism, but in case some of you are, let me just introduce using the 5 minutes that I have. Okay, so usually to formulate classical active system, I think many of you start with a Langevin equation. With a slight difference, I think. If you take the Markovian limit, it's boiled down to Fokker-Planck. Sometimes it's non-Markovian, and in that case, many times, not always, MS Martin Seger-Rose formalism is pretty helpful. Okay? But although you don't bother to do this, at least conceptually, you can write down your total Hamiltonian, including the bath, and then by integrating out the bath degrees of freedom, at least in principle, you should be able to derive the Langevin equation that you have in mind. So we do this more or less the same protocol for quantum open systems. So you start with this system plus bath Hamiltonian. By integrating out the bath degrees of freedom, you get a quantum version of the Langevin equation. And by taking the Markovian limit, you get something that's equivalent to the Fokker-Planck, which is called the Limbat or GKLS master equation, or, this should be a Keldysh formalism, sorry. And you get like a Keldysh formalism. So what's different? Well, obvious difference is, yes, hooray, we have a H bar. Yeah, I think I'm the only one. And instead of being a usual real number, now these are all operators, and also the also instead of looking at the probability distribution, classical probability distribution, to characterize the quantum state, you have to look at what's called the density matrix, where the diagonal component knows about the classical probability distribution, and off diagonal contains some information about the quantum entanglement. But more or less, technically speaking, it's just the Hilbert space got bigger, but not, just technically, it's not that, not that different is a little too strong word, but something like, yeah, it's similar. And I'll just stop by giving you the derivation, very brief derivation. I'll be happy to go through offline about the details, which is a nice 34 pages of fun. So our starting point is this Limbat master equation, which is kind of the equivalent of the Fokker-Planck equation. But where in the usual closed system, perhaps some people remember what's called a Liouville equation in the closed system. But now, because of the dissipation, you have this additional term that describes the decay of the localized electrons in the double occupied state. Now, starting from this, this is written in terms of localized electrons and conduction fermions. But first of all, to derive the effective spin dynamics, you don't want this to be fermion, because fermion can have either upspin occupied, downspin occupied, or it can have vacuum, or it can have double occupancy. So there's, the Hilbert space is a little too large. So what you do is to project out that degrees of freedom, and there's a way that you can do that, and as a result, you get like an effective description of master equation for conduction and localized spin dynamics. Okay, and then after that, the final step is to integrate out the conduction electrons because you don't really care what's going to happen to them. And and by using this Keldysh method, this Keldysh path integral method, and doing some mean field approximation and so on, you get the happily the non-reciprocal interactions. And yeah, I think because the time is over, I'll stop here. And thank you for your attention.
All right, thank you so much, Ryu. I have some questions. Let's start over there.
Hi, Ryo. So very naive question coming from someone who doesn't know much about quantum systems. But so in equilibrium spin systems, you have this correspondence between classical models and quantum models, such as like the 2D Ising model and a 1D quantum, 2D classical Ising model and a 1D quantumizing model with a transverse field. So do you think such correspondences also exist, or can you formulate theories in?
I do not think so, because in equilibrium, or like in the ground state, the quantum system is described by a pure state, pure wave function, and pure wave function psi x have the same dimension as probability distribution px, right? And so I think that's how you can get the correspondence. But here, because you have to look at the density operators, it's pretty different. I mean, it's the space is larger.
Yeah. Thanks.
Yeah. So your final effective equation of motion is isotropic in spin space, but doesn't conserve spin because it's not from a Hamiltonian. Is that right?
Yes, exactly.
And in addition to the decay term gamma, you also have the antisymmetric. That's essentially.
Yes, I mean,
it's sort of an equation you could have written down on pure thought grounds. And what you show is it comes actually out of this formalism.
Yes. But I think I should note that this is a result of mean field approximation, and so I think this contains some artifact because of that arises from the mean field approximation, which is that the spin in these two terms is conserved. But these doesn't, and which means that, let's say you have a ferromagnet, and then if I just, so J, I mean, this is now a many-body system, but J is all ferromagnet, and you shine light to that. I think what you would expect if the light is very, very weak is that it's still a ferromagnet, but this formulation is going to give you S equals
S non-conservation.
Right. So I think some sort of averaging is, it needs some sort of beyond mean field level contribution that adds some terms on top of this, and then that part is something that we don't really have an idea of how to do it.
And what about the noise in that equation? It will also be
I ignored that, and yes, I think the Keldysh formalism can tell you how the noise should look like. And
it would presumably be spin non-conserving also.
Yes, I think so, right.
Christina?
Oh, I wanted to make sure, in your derivation, when you go to the Dirichlet equation, is the bath also treated as quantum?
I'm sorry?
The bath is also treated as quantum, right?
Yes. So, I think I'll elaborate that point. So, firstly, there's actually, if you just look at the localized spin, there's actually two baths. One is coming from the decay. This Markovian bath that, kicks away the double occupied state. But there's another one where the Fermi sea of the conduction electrons are kind of like a bath for them. And so to treat this, the light-induced loss part, I assume to be Markovian. We have a justification for it, we formulate it by like this, and for the conduction electrons, these are by definition a quantum state. So it's not explicit
I see.
here,
So
but
it's
these
half enough.
does contain some information about the Fermi surface effect.
So it's kind of half enough, I guess.
Yes.
Yes. Okay. Thank you.
Jose?
Cool stuff. There's a point that I want to get to, which I thought was really cool. But before I do, I want to acknowledge through a quote that I heard once about nonlinear dynamics, and that nonlinear dynamics is like non-zebra zoology, because there's a whole bunch of examples of different kinds of nonlinear dynamics. And it's the same with non-equilibrium. You can say non-equilibrium, but that means so many different things in different contexts. Yeah. And so I was very much, I guess, pleased and surprised to hear that that our field has something to teach, indeed, in quantum condensed matter about the non-equilibrium dynamics of systems that are constantly being driven and experience constant dissipation. So I want to hear more about that perspective, especially because I trust that there's been other kinds of non-equilibrium dynamics investigated in quantum condensed matter. So maybe you could give us a perspective on that.
Okay, right. So, so there are many. Okay, so how should I say this? Okay, firstly, for solid-state systems, it's basically pretty difficult to drive the system out of equilibrium because it needs a lot of laser power, and it's only recent that people can start doing that. And to my understanding, they're based on they're more considering the transient dynamics. What happens when you pump the system once and see how it relaxes, and that teaches you what the material was. There's another, but that's for the solid-state physics. For the synthetic system, like cold atoms, I mean, where the knobs are pretty different. Firstly, their system is trapped in an optical trap, or so that it's more or less a closed system. I mean, it's almost perfectly a closed system. And because of that, people can ask about how does the closed system thermalize, for example. And there are a very big problem about, like we usually assume that a generic system will thermalize to some equilibrium state in the closed system, but we don't really know why. And there are, cases where it does, there are cases where it doesn't. What's the criteria? There's a lot of open questions there, and people have been looking at those, and there's a lot of development there. There's also this, and this kind of dissipation engine, I mean, there's something called the dissipation engineering, where I think mine count as part of that context, where in cold atoms, by tuning the laser frequency, and there's a lot of lines that the experimentalists can choose wisely to see what kind of dissipation you can get. And there's ideas where by putting dissipation in the very particular way, it gives rise to some fancy states, like topological states of matter. I mean, starting from just Hamiltonian, like even when Hamiltonian is 0, so nothing interacts. By putting in dissipation, you can make the state to become a topological state. I mean, that is a theory work, but I mean, in principle, that kind of things are possible. So there are many ideas that are there. But the connection to active matter has only been started to be studied recently. And I believe that this type of dissipation engineering, considering solid state physics, is a pretty new one. Yeah.
Christian?
Okay. I'm curious about the final equation you showed, like
Yes.
So I guess at the next page, maybe, like when you showed like the density matrix equation. So either way, I guess where I'm going is that from there, like you're writing, you will be able to write some kind of material differential equation that reduces a lot of the things of the functional and everything. All the extra dimensions are kind of like tucked to the side, and you can calculate something, right? So my question is, what remains from the quantum information in that, from the quantum origins of this equation? Like, for example, in a previous life, I worked in nonlinear Schrodinger equation and the nonlinear part has like quantum pressure, and you have some condensation of orbits that you can come out there. So would you find similar things in this
So
final
I
equation?
think, at least because I did a mean field approximation in this step, the only quantum effects that are there is kind of embedded in the in these dependence. So J alpha beta does have information about the Fermi statistics. You know, there's a Fermi surface involved, so KF involved, and also H bar involved. But other than that, I mean, this is an artifact of this mean field approximation. But because of that, that's the only place that
Where you would see
yes, yes. But during the derivation, I think I should point this out. Okay, this is not so clear, I think, but this dissipation, I mean, this type of dissipation where, gosh, this is not so easy to explain, but this type of dissipation does give rise to an entanglement between the conduction electron and the localized electron, and that was pretty crucial in getting this term that is correlated, I mean, in a non-reciprocal way. So yeah, quantum effects are kind of involved in a hidden way, but
right.
Yeah, but
in producing the activity and also in that overturn.
Yeah. Thank you.
Anton?
Could you put a number on this, like how many watts should have my laser, and
Okay,
like
yes.
what should be the
Yes, I mean, that was
the energy of the orbitals and so on?
Sure, yes. Okay, so let me go to the phase diagram that we have. Okay, okay, sorry. So, I mean, this phase diagram based on some phenomenological equation where, again, because of the some artifact that's involved in the mean field approximation, but that aside, this is a phase diagram, and this laser okay, so this is the inter layer coupling. This is the laser intensity, and something interesting starts to go on when this decay rate becomes comparable to okay. So it's oops, there's a typo. This is 10 to the power 8. Sorry, that's a crucial typo. We estimated with that it's a 10 to the power 8 watts per centimeter squared, which is smaller to at least to the numbers that we used. It's 2 digits smaller than where the similar. I mean, there's an experiment. I mean, we look at the literature and saw that it takes about 10 to the power 10 or 10 to the power 11 watts per centimeter squared for the material to start heating up. So we believe that this is 10 to the power 8 is more or less not so bad. Not so bad number. And by the way, we estimated by using some phenomenological model where we computed the localized electron as some damped two-level system, and by calculating how much power you need to give rise to this power, we estimated to be, there you go. Yeah, 10 to the power 8.
Your friend from Atlas hasn't
He's not in the right range of frequency. RPS is something that you putting a laser that and blow that to the electron to the vacuum. Here we are thinking about coupling to a internal degrees of freedom, because we kind of estimated that that's can more easily give smaller required power.
All right, thank you. Next question.
Hi, cool talk. Quick, maybe clarification question or something. So in your projection before the speaker held this, you you traced out some stuff there, right? But did you trace out before that the bath? So, or is it a new thing that you trace? What?
Okay, so the bath. I mean, the truth that I did is to start from the Limbat master equation,
right?
Which is equivalent to saying that you're coupling to a vacuum state, and then I already integrated that out, and starting from that, okay. I think I have a backup slide for it.
This is already reduced density matrix, right? And then you project it one more time.
Yes.
Okay.
Yes. So yeah, I think here you go. Yeah. So starting from this density operator, it's complicated because it's a 2 by 2. I mean, it's a Hilbert space is large because it's a density matrix, but you can split this into, separate this into slow and fast mode, and by integrating out the fast degrees of freedom. I see. Yeah.
Okay. Thank you.
Last question.
Thank you, Ryo, for your talk. I have a quick question about what happens in the chiral phase, let's say, between this metal A and metal B. So in your another paper about frustration, in the classical case, basically your disorder in the system will basically select an orbit. But in the system, is it the same, or is it actually kind of superposition of different?
Yes, I think it's related. So, hang on. Yeah, so where is it? Yeah, so, okay, so on this phase diagram, this solid lines are at kBt equals to 9 milli-electron volts, and the dashed line is some slightly lower temperature. And as you can see, it's not always, but some regime, which in particular here, you get an enhanced chiral phase, which breaks the Z2 symmetry. So, which means that there's like a regime where the noise is enhancing the Z2 symmetry breaking.
Yes.
So yeah, we believe that it is related to that order by disorder phenomena. But it's not, but admittedly it's not as clear as starting from the, from that classical model.
Okay, thank you.
Yeah, thank you.
All right, let's thank Ryo again.